right, I believe this is approximately where we left off. We did start some reaction mechanisms last week, and excuse me, two things of significance that may stick out in your mind from last chapter to what we had discussed last week. What might stick out in your mind? We're talking about saturated compounds and unsaturated. That would be one thing that may stick out. What else? Because underneath the arrow, you have to have what with saturated compounds? In other words, the alkanes. You have to have a catalyst, whether it's heat or UV light. Now, when it comes to these reactions, we notice we got addition of alkenes. Do those have to have a catalyst? Yes or no? You got a 50-50 chance. Those are pretty good odds, really. Is that you asking, or is that what you think I'm going to do? But I didn't hear what you said. So there again, are you sure? Is that all reactions, though? There is one exception. That is true. Okay, it's most reactions. It has something to do with hydrogen.
Like if you have hydrogen, they have to have your...
Well, it's a metal catalyst that you would need. Okay, so that's what we're talking about here. Catalytic, it should be hydrogenation. Okay, not halogenation. Catalytic hydrogenation. When nickel or platinum is used to start a reaction and add more hydrogens. That's just a typing error on my part. Okay. So, one of the things you'll maybe noted that you have seen up on the board, or if you had looked online to see what we're doing this week, which chances are we have not, because we're looking. We don't have school Friday. Whoa! I'm just kidding. Anyway, so we will start talking about what's called Markovnikov's rule. We're just barely going to get into that, and that's important for part of the reaction mechanisms that do take place in this chapter. Okay. So reduction. What we see here. Okay. And when we're doing this reduction, we're talking about adding OHs. We'll get into that at a later time. Okay, so again, we did touch upon this last week. Okay, what does it mean to be asymmetrical? Do you think? Well, yeah, it's not the same on both sides, which would mean diatomic molecules would be the best example. In other words, hydrogen, that would be symmetrical. Your halogens would be symmetrical. But then when we start talking about water or hydrogen halides would be asymmetrical. And then that will lead into with what we call Markovnikov's rule. And we will get into that here in just a few moments. And it is one of your vocab terms, I believe. If it's not, it should be. So 1, 2, okay, we're not too far away. Okay. Because when this happens, it follows a certain pathway. and that only takes place when we're talking about asymmetrical reagents. And I do believe I do need to get out your what's called flow charts, because we will be using those starting this chapter, and you will be utilizing them probably until next. I would venture to say first part of March, and it's something that you can take with you when you take this in college, with the exception of perhaps one of you in here. This will be the last time you ever see something like this. But other individuals in here, you may run across this again. Well, we weren't in the south side of Sioux Falls this weekend, but if we were, we'd maybe go visit the pharmacy, but maybe you weren't working. So,
It was so busy yesterday that it was crazy.
give me some pills. Give me some pills.
All the people were really patient because they saw that we were busy.
So that registers in their mind that, well, it's out of their control. So, okay.
Because it would be like really slow, so like we'd all be working on our own little projects. And then all of a sudden like this whole flood of people would come in. There'd be like 70 people in this. Like at least 10. When you only have like 5 people working.
On a Sunday?
Yeah.
See that?
Yeah, 5 people.
But what do you think a lot of the people are doing on Sunday? Is it renewing a prescription? Because I find it hard to believe there would be that many coming from an emergency room or acute care.
Yeah, I think that's just like a lot of people like refilling it.
Okay.
Within a month or 2 months or whatever. But it was just like so crazy. Like I didn't get out of there until like 6:21. When I was supposed to get out by like 6, but it closed at 6. Some of my other coworkers didn't finish one of the projects they were supposed to be working on, which was kind of frustrating because like I had said to her, she's like usually the cashier anyway. I had said to her, I was like, if you want to count down registers, I can do like the called waiting unit, which like takes inventory on all the people we have on the shelf.
Okay.
Which I can do that really fast by myself. But she's like, no, you can count down registers faster than me. Like I can do this. We're probably not gonna get it done though. I was like, she's not trying to get it done. Then the boss says, you guys can't leave until we have that waiting and bid report done. And they weren't even like halfway through yet. They weren't even a fourth of the way through, and I was like, so I wonder how advanced she let me go home.
Are you the only person working there with your level of education?
No, there's like 3 of us.
Okay.
And the one was my age.
Do you get along with them then?
Yeah. Yeah, but like also, I mean like I can take it, but like okay, well I don't mind her. She's not like a bad person, but her first impression on me was she asked me what sports I played because she knew I played sports. So I said like volleyball.
What you're doing is required skill, but it's also an acquired skill, if that makes sense. Not everyone can deal with people. That's an acquired skill. In other words, you have to do that. And yeah, it's also required. But do you ever lose your patience with, do you have to answer the phone?
Well, we have like a drive-through and I have to answer the phone back there, but like I don't have to answer like the actual phone.
Okay, because I've stood in line and there's been pharmacists or college students having to answer questions, and you can tell they're visiting with someone who's maybe hard of hearing and they're repeating themselves over and over again.
Drive through, if you don't pick up the phone and it's windy, you can't hear them. So you want to try to avoid asking them to pick up the phone because, like, if they wanted to pick up the phone, they would have. And some people are great and they pick up the phone, but other people it's just like, all right, so like, how do you spell your last name? What's the date of birth? You ask them over and over and over again, and I was like, just pick up the phone, please. Like, I can't hear you.
Okay.
And then they get all mad because it's like, how come you said you were the first 79? Well, I can't hear you because the wind's blowing outside. So
It it's your fault.
always my fault.
Uh,
There was one time we had this lady coming through the drive-thru asking for needles, and like I'm not very good with needles, like picking out because like there's so many different like sizes and like
Okay.
lengths and stuff like that. And so I asked for one of like the technicians. I was like, okay, so I need this size, this length, whatever. And he's like, are you sure that that's what they needed? And I was like, well, I can listen, like I know what they said, I just don't know which ones to grab out. And so he asked her which one it was. She was kind of like, she was already like not very happy. And then we couldn't find them. So like I looked for the needles, but I just couldn't find them. And then he couldn't find them, so we asked the pharmacist, and the pharmacist asked which size needles she needed. And then I was like, you can hear her through the phone. She's like, oh my god! And I was like, Gail, we told you what size needles she needed. It was rough. And we're not supposed to get needles from the drive-thru. Unless I guess she has insurance probably, but like, because that's where all the drugging come. Needles through the drive-thru.
oh my god.
Why do insurance check the phone rules? Gail, why do you ask her that? Oh man, it's a rough day. Uh,
Okay. Okay. Anyway, I shouldn't be spending so much time listening to your conversations because we're avoiding the other two.
it was a bad day at work, guys. I'm just saying.
Anyway, okay, so we want to get to this one, and we're going to go through some reactions that'll take us through uh, what I want to cover. We'll go through again some of these reactions. But in the back room, you actually have pharmacists probably mixing up different types of cough syrup pending the doctor's orders, correct? Yeah. Okay. But I just find it hard to believe that any pharmacy has everything that is needed. So I would be led to believe that sometimes they may say you have to visit the pharmacy at the hospital, maybe.
Otherwise, you can't get any purchases.
Does that seem kind of
Next day, so like you have to wait.
okay? So what we see happening here is when we're looking at this rule with these reagents. Okay, when we say the hydrogen Okay, that's what we're talking to. Asymmetric reagents added to an asymmetric alkene. The major product is this should be, I just have H. Okay, so it should say hydrogen being placed where there is the most. And what we mean by that is the most hydrogens to begin with. And that won't make any sense until you see it. Okay. Okay, does everyone have this wrote down that wants this? Okay, so this is another one of them aspects. You're writing this down and you really don't know, well, what does some of this information mean? And I really don't know if I could specify any better verbally speaking it, but once you see it, then it will make sense. Okay, so remember, we want to classify these as symmetrical. This you don't need to write down. Okay, and then, so these are reagents that we're referring to. So give me an example then of the symmetrical reagents. There's about 5 you could give. Remember, that's the same on both sides because it has symmetry. That's one. So again, you could write H2 or H to H. Okay, so it's the same on both sides. What's another symmetrical type? Okay, so we'll just do chlorine to chlorine. Yep. So what you're catching on to is it's all the halogens are symmetrical. In other words, it's the same on both sides. Now, the asymmetrical type, however, means what then? That is not the same on both sides. Okay, so we mentioned what they were today about maybe 5 to 10 minutes ago. Water is one of them. Now, it looks like it is the symmetrical type because you look at it in that fashion, but when you use your physical science or general chemistry skills, how would we determine that this is the asymmetrical type, not symmetrical? Because what ion do we see in this molecule? What's this one right here? OH is That's a hydroxyl group, but that's the organic reaction. It's a hydroxide ion then, to where when we break that apart, this side's +1, that side's -1. Okay? So that is the asymmetrical type. And then there's a whole bunch of other ones, like this friendly one. Yeah, it's going. Saying hi. Hydrogen iodide. So my point is it's a hydrogen with a halogen. Any one of those then would be the asymmetrical type. Okay, so what it boils down to with these reactions then is, first of all, what type of compound do we have? Is the compound symmetrical or asymmetrical? Is the reagent symmetrical or asymmetrical? So, give me, let's say, we'll show you both types. We'll do butene and 2-butene. Okay? Okay, there's butene, and then right below it we'll go ahead and do our 2-butene. Oops, I did that wrong. Okay, so we'll go ahead and take one bond out of here. And how we want to label that is the bottom compound is the symmetrical type.
The athletic trainer is here. If anybody needs to see it, we go to the training room, please. The athletic trainer is here. Thank you.
Okay, so this is the symmetrical type. This is the asymmetrical type. Now, when it comes to asymmetrical compounds, those are ones that has the double bond after the first one. Okay, it doesn't matter how long this chain is. This can keep on repeating, and as long as that is on the end, okay, this is the asymmetrical compound. Okay, and same thing here. It doesn't matter if there were 4 more carbons on this side, you would have 6 on this side and only 2. This is still considered as being symmetrical. Now, you might think, well, that doesn't make any sense. But there again, this goes back to what we call Markovnikov's rule. Okay? So, give me an asymmetrical reagent, any one of them. Okay? So we can add water. So we'll go ahead and do that to both of them then. And I think it's easier to see if you write it like that as opposed to H2O. You want to add it to both, or you want a different asymmetrical compound? Say that again. Just add it to both. Okay. Oh my gosh! Yeah, that you were supposed to say, "Oh my gosh!" Didn't you hear me the first time? I'm sorry. That story was a good one. So, okay. So, when you read what Markovnikov's rule had said, the hydrogen gets placed where there was the most. Okay? What the author goes on to say is I don't like looking at it this way, the rich get richer. While it does in the manner of what we would say hydrogens, that's what determines where these compounds or these molecules will attach. Okay, so we know that that's where these split apart between those two. We knew that from the inorganic class, and we know it now from the organic class. So we do not have to have a catalyst because this will react. Okay, we're not adding just hydrogen, so we don't have to have anything there. So now when we look at these, are these saturated or unsaturated compounds? Unsaturated. So these double bonds break very easily. Okay? So we're going to go from an alkene down to an alkane. So what I want to do is I like color coding these because I think then it's probably easier to see. Okay. So we'll go ahead and put all of the same hydrogens in that we had from before. Okay, and then we can do the same thing here. Okay. Now, when we say the hydrogen gets placed on the compound that already had the most, that Markovnikov's rule is only going to apply to this top one, okay? Because this hydrogen is looking for, on this compound, which one had the most hydrogens to begin with. Is it, got to find your double bond, was it carbon 1 or carbon 2? How many hydrogens are on this carbon? How many hydrogens are on this carbon? 2. It's got 4 bonds, but only has 2 hydrogens. How many hydrogens are on here? 1. So that means, according to that rule, this hydrogen is looking for the carbon that has the most hydrogens on the double bond. That's what Markovnikov's rule is saying. So what that means is that, is this going to attach to carbon 1 or carbon 2, do you think? Which one has the most? Carbon 1 does, so what that means is that hydrogen then goes here, okay? Then what's left over in this reagent then? In OH. So now we went from an alkene to forming a what? An alcohol. That's right. And when we get further down the line, okay, this mechanism, you're going to be using these reactions from here probably till the end of the semester, these types, okay? Because this is going to be what we call a secondary alcohol. We don't need to know that right now, okay? The same thing happens, you could say, does Markovnikov's rule apply to this? Well, find your double bond, okay? This carbon has how many hydrogens? 1. This carbon has how many? 1. So the difference then is when that double bond is on the end, that's why this follows Markovnikov's rule. This one, however, does not. So therefore, it does not matter where you put these bonds then. You can go ahead and say, well, I'm going to put this hydrogen down here and this OH up there. Okay? I mean, that's fine, but it doesn't matter. You can flip-flop the two. Because notice we had the OH go on this one, the hydrogen on there. We can flip-flop them and say, well, I'm going to put the OH on this one and then just the hydrogen on that one. Those form in equal amounts. Okay? But you may remember, so if you have the symmetrical compound, even with an asymmetrical reagent, this only has one product. One product only. Okay. Well, you might say, well, what about if you flip-flop them too? Well, you can. Even if that chain is longer, it's only going to form this type of compound. It would be in equal amounts, whether, let's say we had another 2 carbons on here. So notice we would go from 1, 2, 3, 4, 5, 6, from 3 hexanol to 2 hexanol. Those form in equal rates. But don't worry about naming that, okay? Only thing that you ever had to do up to this point was just recognize whether this was an alcohol or not. We don't need to name these yet, okay? So we're going to review this again tomorrow, but the last thing I want to do, okay, is if you remember from last chapter, there were there were alkanes that underwent reactions that had 2 products. They formed in equal amounts. But what we see here, this is the major product, okay? And this also forms a minor product. It would be the same thing with number of carbons. But the difference is then this is the minor product. Okay. So the conditions have to be right. You have to have an asymmetrical compound, an asymmetrical reagent, then that gives you 2 products, and you have to account for both of them. So about 95% of the time, you get this. 5% is what you're going to get with a minor product. From last chapter, it was like 44 and 37 or something to that effect. It formed in equal amounts. Okay, now, that was just brand new to you. Tomorrow, we'll grab the books. We'll go through some of the the rules that go with naming these compounds and some more of these reactions to get better practice on them. That's where we'll stop for today and pick up tomorrow.